Hey physical science students, this is Dr. B and we are in activity 3 for what are our choices for supplying energy for the future. It's part of the High Adventure Science series in Concord Consortium, and we are working on activity 3. So we're going to start out on page 1 here, historical production of natural gas. We're going to try to figure out where to find that natural gas. We're going to use a process called hydraulic fracking to release natural gas from deep in shale formations. So historically, you can see that natural gas production, this has skyrocketed lately, and that's because fracking has started and making it easier to get natural gas out of places previously have been inaccessible. And you can see that the shale gas here, this is total gas, and shale gas is the blue here. So shale gas is probably responsible for most of the increase in production of natural gas overall. Natural gas is what heats our homes here in the Midwest. Somewhere in your building, you probably have a furnace burning natural gas that either pushes hot air around your building, or in some older buildings like mine, you have radiators and it's pushing, that furnace is heating up hot water and pushing that around your building. So we studied the graph, what accounts for the increase in natural production after 2005. If we look at this blue line, that's a clue. That's why the green line is climbing so much. These other lines are natural gas. The brown, the red, and the yellow lines are natural gas from other sources, and this green one's the total, and they're wanting to know what is contributing to this total increase here in natural gas production. So I'll let you make a decision there. So shale gas comes from shale deposits. Shale is a sedimentary rock composed of small particles of silt and clay laid down over many years. Have you ever walked in a really muddy, mucky lake where your feet sank right in? That's what makes shale when it's compacted over a long time. Shales are formed in slow-moving water, such as ancient seas and lagoons. The fine particles precipitate out of the water and get compacted as more and more weight is added on top. The picture shows a piece of shale. Note the striations in the rock, the lines here that show the layers. Natural gas is found trapped within shale formations, and that's called shale gas. You can get natural gas other places, but the stuff that's stuck in shale layers is called shale gas. Some sediments and rocks are very porous. They have lots of spaces for liquid and gas, and others have very little space for liquid or gas. They're non-porous. So when we want to think about where we're going to find natural gas, we're going to find natural gas in rocks that have high porosity. And you can see, I'm going to demonstrate here with this jar of marbles. If you put marbles in a jar, there's plenty of room for other stuff to be in the marbles. You could pour a lot of water in here still, and there would be room for water between the marbles. So porosity means how much room there is inside the rock. A jar of marbles has pretty high porosity. If we wanted to put something else in here that's smaller than marbles, we could do that. Permeability is how easy it is to go through something. If we wanted to create an ideal storage for natural gas here in our jar of marbles, we could put some modeling clay, which is impermeable, on top of, inside the jar on top of our marbles, and that would trap the natural gas inside the marbles and keep it there. So that's what we want. We want high permeability so we can store lots of natural gas in our rock, and or high porosity, high porosity to store lots of natural gas, and low permeability. We want a nice big thick piece of clay or some kind of rock that isn't very permeable. So we have this nice layer of impermeable rock on top of all the natural gas so it can't leak out, because we can't really go in there and get it if it's already gone. If it's formed and then leaked out, it's no good to us because it's gone. So we want to put something that's impermeable, or we want to look for rock that has something impermeable on top of the natural gas. Impermeable just means you can't pass anything through it. So the questions 2 and 3 are asking you about the ideal porosity, the space that can hold liquid or gas, like the space between the marbles, and their permeability, how easily something can pass through. Modeling clay is pretty much impermeable to water. You want to think about it that way. So let's go to the next page here. Known reserves of shale gas. The map shows the locations of known shale reserves throughout the world. Here in the Midwest, not so much in Minnesota, but we've got some on the East Coast and down in Texas. There's also some in North Dakota, which is known as the Bakken Shale. The geologic history of those areas, it's telling you that there were shallow seas in those areas at one point. Everything in this picture here was a shallow, that's shaded red, is a shallow sea where that shale, those fine particles could accumulate in shallow water and get squished down and make shale. Shale formation is, you can see what was underwater if we go, this is the current view of the Earth. And if we go 14 million years ago, we can see that most of what we know is still above water. If we go 50 million years ago, still looks pretty familiar. But as we start to back up in time here, 66 million years ago, you can see that part of the North American continent, like right where the Bakken Shale is in North Dakota, would be underwater. And you can see more of North America is underwater, especially this line of where the shale is. And that's a good indication, we know, for if there was a shallow sea there, that's where we're going to see shale. The Marcellus Shale, which is found in the northern end of the Appalachian Mountains, that's on the east coast, was formed during the Devonian period. The Appalachian Mountains did not exist during the Devonian period. What did that area look like during the Devonian? Well, let's see if we can go back to the Devonian here. It's Middle Eocene, KT boundary, Late Cretaceous, Late Jurassic, Early Jurassic, Early Triassic, Permian, Carboniferous, Devonian. Most of North America was underwater. And so the Appalachian Mountains weren't formed yet. The Appalachian Mountains formed when another plate slammed into the North American plate and crumpled it. And so the Appalachian Mountains are here, that when that plate crumpled, it made mountains. But it was underwater, and then as it collided with another plate, it made mountains. So the graph shows the depths and temperatures that are necessary to turn organic matter, basically dead stuff, dead plants, dead animals, into oil and natural gas. It's a pretty narrow window here. We want the gas to not have water in it. We want to have a very specific temperature, and we want to have a very specific depth. So that helps geologists guess where that gas is going to form and where they should be drilling. And that's going to help us figure out where we should be drilling in some of the next pages here. Question 8 is when the shales that now contain gas were formed, there was no gas in them. The natural gas started out as organic matter, and then it rotted. And we can still see rotting things producing natural gas in a swamp. They're underwater, and sometimes we see bubbles released from under the water, and that's plants and animals in the swamp turning into methane and evaporating out of the swamp. It can, not evaporating, rising out of the water and leaving the swamp. That happens because bacteria are breaking down some of the components of the dead things and turning them into methane. It doesn't get stuck in the swamp because there's no layers, thick layers of sediment over the dead stuff. Natural gas will only form if there's a impermeable layer over where the methane, the dead stuff, is rotting. So that impermeable layer would be like a clay layer, a sediment layer. So if you want to get gas from shale, you have to drill for it. If it's in, because that shale is down under the surface. So we want to use this model to drill for shale. We're going to explore the process of horizontal drilling and hydraulic fracturing to release natural gas from shale layers. Now, unfortunately, this doesn't work on an iPad, but if you do have a laptop, it'll work. So there is, inside the sim, there's a down drill button, and we're aiming for this layer here that's got the red dots in it. That's going to help us. And then we can just kind of hold down the vertical drill here until we get where we want to go. And then I'm going to drill sideways from here. That's called horizontal drilling. We're going to use explosives to crack open the rock. We're going to fill it with a fracking fluid. Some places use water, some places use propane. That opens up the cracks, forces them open, and helps release more natural gas into our well here. And then we're going to pump out the fracking fluid. So we've done a couple of steps here. We've drilled down, we've drilled sideways, we've set off some explosions, we've filled it with water, we've pumped out the water, and now you can see our production here has gone way up. It's good for, maybe a year or so, and then it starts to decline. If you think about it, it's kind of like a can of shaken soda. If you've ever shaken up a can of soda, or someone did it as a practical joke, which is really mean, don't do that to anyone. But sometimes it happens, you're walking around, it's in your backpack, and you open it, you forget you've been walking around with it, and it just, all the soda comes out at once. And then there's a little bit left in the can because there's no more soda to push that out. And that's basically what happens with the natural gas. It comes out all at once because there's gas down below pushing out the gas at the top. And then once you get most of the gas out, there's nothing left to push it out. So you can answer question 9 and question 10. You can see once we pump the water out, it hangs out in a hydraulic fracking pond right here. They put it in a tank because it may or may not be contaminated, and they don't want it mixing with the groundwater because people drink groundwater, and if it's got stuff from being in the pipes here, we don't want to drink that. So how do geologists go find that shale with gas and oil? Well, most of them have a map from lots of geologists have cooperated over more than 100 years collecting different kinds of rock at the surface, and also drilling down, and that helps us kind of guess where we might find shale. We don't know exactly where it is until we drill. And that's the point of the next simulation, is we're going to drill without seeing, because geologists don't have a nice, tidy little map of what's underground. They're just guessing. And they're drilling and bringing stuff up and looking at it, and drilling and bringing stuff up and looking at it. So they're just kind of going and guessing and guessing and looking and guessing and looking and guessing and looking as they drill. And if they hit shale, great. If they don't, then you might lose your job as a geologist for the gas company. So let's do it blind here. I don't know what the shale is going to be. You can put up to 3 wells in your simulation, and so I tend to start on the edge. Oh, there we go. So I've hit the shale. I see these little red dots. I'm going to drill sideways now. Hopefully I'm still in shale. Oh, there, I kind of got out of the shale, so I'm going to stop. I'm going to set off explosions. I'm going to fill with propane this time and see if that's better at forcing those cracks open. Propane is a gas. It's those tanks that you use with a gas grill, or maybe you've cooked with propane inside an RV or a camper. That's what's in those tanks, and they also use that for fracking. It's a little bit more expensive for water, but it can be cleaner, because then you don't have to use water and get it all dirty. We're going to pump out the fracking fluid, and we'll see what happens. Oh, we did pretty good. We can see that all the methane, all the natural gas comes out really quickly, and then this kind of tails off. If we want to drill another well, we could do that on the same fracking pad, and then that would increase our overall production. I'll drill a well right here. See if we can get up our production here. So this is well number 2. It's going to show up as a green line on the graph. I have to be careful and kind of creep down here. I'm going to try to drill left on top of the other well, hoping the shale layer kind of extends there. I'm going to set off my explosions. This isn't going to be as efficient because I'm guessing the shale layer kind of ends right here. We'll use propane this time. That's pretty good. We've got some cracking here. We've got a lot of this green area. That means we'll probably have made a lot of cracks, and we're doing okay. Oh yeah, we did even better than the last one. We got over 809 something, 900 something here. You can see that the red line is our first well here, that first well, and it's really tailed off. It's not making much natural gas anymore after about 30 years. And our second drilling site is not producing much after about 5 years. So you can answer questions 11, 12, 13, and 14 on your own. As technology advances, scientists can see Earth's layers with increasing resolution, which brings about the next technology, and so on. The cycle has led to the development of 2 technologies that made it possible to extract natural gas from deep shale deposits. Hydraulic fracturing, so pumping stuff down and blowing open those cracks, and horizontal drilling, so you can drill not just down into the layer, but you can drill sideways, which seems pretty crazy to me. Hydraulic fracturing was first used in the United States in 1947. This technology allows drillers to fracture the shale, letting gas move towards the surface freely. Hydraulic fracturing involves pumping a liquid or gas, often water, carbon dioxide, or propane, into the shale formation. Shale deposits are horizontal, they're a layer, arranged. Previous drillers were only able to drill straight down. The ability to drill at an angle allows more shale to be accessed than could happen with vertical drilling. So you drill down, you drill sideways, you make explosions to make cracks, you pump stuff into the cracks to blow them open a little bit more, and you try to get all that natural gas from that shale layer to come to the surface. It's a controversial hydraulic fracturing, where you use water, is controversial because you use a lot of water, you dirty it up, and then nobody really knows what to do with it afterwards. If you release it back into the water table, it can put contaminants in the water table. Steel casing lines the well and is cemented in place to prevent any communication up the well bore as the fracturing job is pumped or the well is produced. Shallow formations hold fresh water that may be useful for farming or public consumption, are separated from the fractured shale by thousands of feet of rock. How does the combination of horizontal drilling going sideways in the layers and fracturing, explosions and pumping in water or gas to widen the cracks, allow drillers to extract the natural gas from the shale? You can answer question 15 on your own. You want to hit show all answers. And you're going to come to a place that looks like this. When you're done, you're going to copy and paste everything on this page. Just use your finger to highlight everything. And then you're going to copy and paste it to another document. When you get it on another document, please highlight your answers. Again, please highlight your answers. Copy and paste to either Notability or Google Docs or Word. Assemble activity 4, 5, 3, 4, 5, and 6, all in the same document. Highlight your answers and turn that in to Lab 5.2. Thank you so much. I'll see you for activity 4.